Okay. Okay, so today I'm going to be talking about the cost of abstraction. This can mean a lot of things, obviously. I've already had a few people come up to me and sort of suggest different, dimensions with which this can be discussed. So hopefully this is something that's interesting to most people in this room. Just as a quick background to introduce myself, my name's Cameron. You can feel free to add me on Twitter and LinkedIn. I'm a principal machine learning engineer at Simple Machines. Simple Machines are a software consultancy based out of Australia. So you probably haven't seen us around in Canada very much. And we work on basically data systems in general. So we've got streaming data systems, data platforms, big data systems, machine learning systems, all that kind of stuff. And I'm also fairly recently an open source contributor with some Scala Z projects in the analytics and machine learning space. So before I get started on the cost of abstraction, can I just get a quick show of hands who here has heard of Final Tagless before? Okay, so quite a few. And who's used it in production? Okay, awesome. And what about Free Monad? Has anyone used that in production? Okay, so only a few. Okay, cool. So there's a few different abstractions that you tend to see in this space of effect handling and sort of structuring your programs, and they're very commonly Final Tagless, Free Monad, and F Monad. I'm going to focus primarily on Final Tagless and Free Monad in this talk. So first of all, to understand the motivation for these different abstractions, I'm just going to quickly introduce what effects are, and then sort of how these abstractions help with structuring our effectful programs. And then we'll go into some of the performance impacts of using the different abstractions. So an effect is defined as a change which is a result or consequence of an action or other cause, assuming that you take the Wikipedia oracle as the definition. So to see what this actually means in something like Scala, say we have a function toDouble and it takes a string and returns a double. This can be fairly trivially implemented by simply calling toDouble, and as we expect, if we pass in an actual double, we would get back the double that we expect. But if we pass in something that's not a double, a string that doesn't conform, this will blow up, and it will probably blow up with some kind of exception. So a very common pattern in functional programming and Scala in general is that you want to actually capture these effects. So this is a side effect of potential failure. So we might have some effect in its generic sense, and more concretely it might look something like this. We might have a try that wraps this computation. If it succeeds, we give it a success. If it fails, we give it a failure. And this means that we can now work with that effect as a value, and this is a very common pattern in Scala. Now, it doesn't necessarily have to be the underlying effect that caused the change. So for example, in this case, we're exposing it as an option, whereas it actually was throwing an exception. We just discard the exception in this case. And it turns out that there are a lot of different types of effects that you can use. Most of the ones that we're probably familiar with are monadic effects. So you're probably familiar with futures, tries, and options. They're all in the standard library. There's some more advanced ones like reader, writer, and state, which let you kind of do, passing in a context for readers, doing some kind of logging of some sort with writers, and doing stateful computations with state. And as Harmeet showed before, we've also got these things called monad transformers. And what they do is they kind of let you combine these effects in a way that lets you work directly with the value that's nested inside the effects without worrying about how you combine and sort of flat map and map through the layers. Now, this is all well and good, but what I found personally is that once you sort of learn all this theory, it's not entirely clear how you then apply that to structuring your programs and how you start using these effects. So if we sort of take a step back and think about what our basic domains might look like. Let's say that we have a user domain that just has a single user and it's got some functions that will act on a user. So that might be create user, it might be get users by ID, and it might be list users. When we actually go to implement this, it looks something like this. It's basically just a subclass in Scala, and you basically, where the question marks are is where you'd actually give the implementation details. Now, you're probably looking at this going, yeah, okay, that's nice and idealistic, but this doesn't look like something I'd actually use in a production system. And so you might say, I need to capture failure. My methods can throw exceptions for some reason. I want to capture either it's a throwable or the actual result that I care about. And then you might sort of look at this again and say, well, I want to back this with a database, and I don't want to hold the connection, so maybe I want some kind of asynchronous effect. And so you might add in something like a future or a task. And this is where monad transformers become quite nice. You can actually combine them into a single effect type. Now, if we take a step back from where we started in terms of modeling our domain, we went from something that is modeling the exact essence of the domain to something that has all of this extra stuff around it. And that extra stuff is actually what happens when we conflate our implementation effects with our domain. So we want to be able to write our programs with effects, and we want to be able to manage them, but we don't want our domain to become polluted as a result. And this is exactly where things like final tagless and free become really useful. So final tagless, first of all, if we start off with that same initial domain, what it looks like is basically the exact same thing, except we're saying we have this higher kinded type F that will basically wrap our return types. So we're basically declaring that there is some type of effect on all of our return types, but we're not going to commit to what that effect is yet. And then when we actually implement these interfaces, we can choose what that effect is at that point in time. So for example, here we've got the future user repository, or task user repository, I probably should have called it. And that basically implements these methods in terms of task. And you can imagine doing this with any type of effect. And the nice bit is that this defers it to the subclassing point. So we can write our programs in terms of that abstract F, and then we can worry about how we want to interpret it. So we can do some really nice things in terms of constraining F. So if we're writing our programs in terms of this abstract F, and we want to do some kind of sequential operations, like with a for comprehension, we might want to constrain it to a monad. Or if we want to do things in parallel, we might want to constrain it to an applicative, for example. And so the usage might look something like this. There's 1,000,001 different ways you can write this stuff, obviously. But basically we say I want to do 2 operations. I don't want to commit to a specific implementation of F yet. I don't want to tell you what my effect is, but I want to be able to say I'm going to have a flat map that sequences these 2 things. And so that's why we've got this type class up the top of monad that is constraining F. And then when we actually use this thing, we can say I've got a new future repository and I want to run it using this create and list, and we just pass in the repository. And all of those, F basically at that point becomes a future. Future will have a monad instance. I think it's not a particularly lawful one, but there are instances out there. And that will actually then give us back the users of future list user. Now, the nice thing about this is that we can swap out that implementation at any point for any other thing that is a monad. Now, the other thing about final tagless in terms of performance and in terms of its implementation on the JVM is it has almost no overhead, as if you were to actually hard code it as just a future. So if we went back to this interface, if we had actually just written future everywhere that it says F, it's more or less the exact same performance cost. There's only one extra virtual call, as far as I can tell, in the bytecode. So that's quite a nice property. Now, as for the free monad, so the free monad is more or less it's solving the exact same problem as the final tagless approach. It just does it in a very different way. So what it does is it actually reifies the domain. And what this means is that we're actually making our domain concrete. So the way that we do this in Scala is we represent our domain as an ADT rather than as a trait with methods on it. And you can kind of see the parallels if I put them side by side. You've got final tagless at the top, where we're saying we've got some effect F that we want on all of our return types. And with the free monad encoding of our domain, we've got the same F here, and that becomes the things that we extend. So it's just a sort of quirk of how you have to do this in Scala, but fundamentally it's the same thing. Now, free monad basically works by lifting operations into the free monad structures and then flat mapping between the operations. So you can imagine if we use those data constructors, create user on the previous slide, and then we create, say, Steve, and he's 23, then we do a lift. That lift will pull it into the blue box, which is the free monad. And then if we've got multiple things inside free monads, we can actually flat map between them in order to basically create a program that is the sequence of these steps. So in order to lift our domain into the free monad, we just have a little bit of boilerplate, and there are frameworks that automate this stuff if you don't want to do this. I personally tend to prefer writing it by hand just so that I've got a bit more control over how it works. And all it really does is just call these default methods free.liftf, and then you pass in the actual data constructor. Now for the usage, it's more or less exactly the same as final tagless. You can see here we've got free, and it's got the user operation, which is our effect type. And then we've got list user. So just to point out as well, that user operation, that's just convention that I've noticed in most code bases. You can call it whatever you want, really. It's just models the effect type. And then we create our interpreter. Now the interpreter in the free monad is akin to a subclass with final tagless. So remember we had future, what was it called? Future user repository. So that would be the same thing as this future interpreter. It's just got a slightly different way to do this, and it's using what's called a natural transformation. And what that's doing is it's saying, give me the user operation effect type, so we can think of that as F as well. And then I want to turn that into a future. That's effectively, conceptually what it's doing here. And so what we do is we get this FA in the apply, and we will do a pattern match on it, and it will have all of the different operations that we have in our domain, which in this case will be our create user, get user by ID, and list users. And then we can just implement it as if it were methods in final tagless. And then finally, when we execute it, we basically just say create and list.foldMap, and the fold map will go through and it will apply our interpreter to each one of the steps in the free monad. Now, the other thing I mentioned with final tagless was that you had this monad and you had applicative, so you can constrain that F at the time of declaring the interface or at the time of usage. You can do the same sort of thing with free. It's a little bit more cumbersome to combine them together. If you want to do, say, free monad and free applicative, you have to use two separate structures to do this. And this is very much possible. I've done a talk earlier in the year if you're interested in how to do this kind of stuff. But it is a little bit more cumbersome. So the next step that we need to sort of start to understand a little bit more is the JVM layout and how this is going to affect some of the stuff that we're going to talk about. So every method call on the JVM is going to create a new stack frame. And then we've also got this other area in the JVM called the heap. And you're probably aware that's where objects are created and the life cycle is managed with GC and all this kind of stuff. Now, in functional programming in particular, you tend to get a lot of problems with stack overflows because every time you call flatmap, for example, it's actually popping a new thing onto the stack. So the free monad was kind of brought along and developed to solve the problem of this by pushing those calls onto the heap rather than onto the stack. And it does this using a thing called trampolines. So a trampoline is basically, at a very high level, a suspension or completion of a computation encoded such that it bounces off the heap for every computation. It also has, for the free monad, it also has a flat map constructor to make it monadic. There's a fantastic paper by Runar called Stackless Scala with free monads, if you want to learn more details about that. But it basically just generalizes the type constructor. So the trampolines are parameterized on function 0, whereas free monads, that function 0 just becomes a generic higher kinded type. So just from seeing this kind of stuff, we can see that the free monad is clearly doing more work at the JVM level than final tagless, but how much of a performance hit are we actually going to take by using one over the other? So I sort of dived into the world of benchmarking. I'm certainly no expert, but it turns out there's a lot of depth to it on the JVM. So what I thought maybe initially we could probably do is something like this, where we get a timestamp before we start a computation, we run the computation, get a timestamp after, and find the diff. And for statically compiled languages, this actually is not a terrible idea, but for the JVM, it is a terrible idea. And it turns out that there's a lot of reasons for this. So first of all, the JVM heavily optimizes a lot of things in your original code. And much of this happens at runtime via the just-in-time compiler. And quite interestingly, the just-in-time compiler is very clever, but it uses a lot of heuristics. So there are different types of method calls. What are they called? The megamorphic, monomorphic, and bimorphic. And if you are, say, running megamorphic calls, which is when you've got lots of different types coming through and it sees one type coming through, I think it was about 10,000 times in a row, it will actually optimize the bytecode that the code that it's generating to assume that that's the case. And then things will start running a lot faster. And then as soon as it gets something that isn't that same type, it goes, whoa, hang on a second, this is not right, and it will undo everything and your program will become really slow again. So you can imagine if we're trying to benchmark something in a predictable fashion, these kind of effects are going to really change what our benchmarks are saying. Now on top of this, because it does so many different optimizations, it's really hard to isolate the thing that you're trying to test. There's very often a lot of different things that are happening on the JVM and in the just-in-time compiler to make your program run really fast and improve its speed over the execution lifetime. And as a result, it's also quite hard to generalize from benchmarks because you take away so many of the things that you will actually get in a real program to sort of isolate this one part of your program that it's probably not necessarily representative of the way it's going to be used in your code. So just keep in mind with all the benchmarks that I talk about here, they're testing a very specific type of usage, and they may or may not generalize depending on what your usage of these things is. And I'll try and make that as clear as possible when I'm talking through them. Now, as for the optimizations that the JVM does, as I mentioned, there's things like loop unrolling, there's method inlining, on-stack replacements, dead code elimination, which is actually a really tricky one for Java when you're writing benchmarks, and Scala, sorry. Basically what this is the JVM will look at your code and it will say, if you haven't used this piece of code, I'm just going to throw it away. I'm not even going to execute it. And as a result, it can look like something is running super, super fast, but it's actually because the JVM's too smart. And then there's all these other things, constant folding. I think I looked it up and there were like 3 or 4 pages worth of stuff that the JVM does, and that's kind of just like the high level. So you can understand that this is really complex to try and do yourself and to control all the effects that could be happening. So benchmarking 101 for the JVM is to use JMH. And this basically is the framework for writing benchmarks on the JVM. It's commonly used for micro benchmarks. They stress a specific piece of code, and we'll see what that kind of looks like shortly. But basically, you don't want to be testing like an acceptance test level thing with this, because there, as I mentioned, are just too many effects that will actually affect your benchmarks. And they generally do a pretty good job of helping you to avoid a lot of the unwanted JVM optimizations, but you can also kind of enable them implicitly if you want. So I've kind of had a fair few questions in the past about free monad and final tagless and f monad and a few different effect types. So I thought what I'd do is basically compile together a list of the different things that people had been kind of asking me the most about. And I've got f monad only with one up there, and I'll explain why shortly. But the main ones that I was trying to test was between final tagless and free monad, and it turns out that cats and Scala Z have a slightly different implementation as well, if that's important to you. But it certainly has had some very interesting results. And I wanted to test across a few of the different effect types that you're actually interpreting into. So for benchmark options in JMH, I ran it with the the benchmark mode as throughput. This basically just means like how many things happen in some time period, and that time period was in seconds, and the whole thing's running on a single thread scope. So I ran each of the benchmarks I'm about to show you by constraining it to a single thread, a single JVM fork, 25 warm-up iterations and 25 actual iterations. This takes absolutely forever, but it's worth it to get more accurate measurements. So I think it took about 3 hours to run these ones on my Mac, which had a 4 gigahertz i7 and 24 gig DDR3 RAM, if that's important to people. And so this was the results that I got. Now I haven't got numbers on here just yet, but these were the relative differences. And I'll sort of step you through from the slowest to the quickest and explain what the benchmarking was actually doing in each one. So first of all, the sort of slowest group of them was the F monad. Now, I'm not necessarily an expert on the F monad, so I decided it's probably best to not paint it in a poor light without giving it its fair shot. But the code that I managed to sort of get running and compiling and working was certainly an order of magnitude slower than everything else. In terms of the free monad, so I'll give you a quick view of what the actual benchmark was and how it ran. I created an ADT, which is, again, describing the domain of the problem. In this case, it was a calculator. So the calculator is just able to do add and a get. So all it can do is add numbers or get them back. And so there was a simple implementation of this calculator, which had an internal var as its total, and it was able to then just add and get from that total. So I didn't want any of the effects of functionally adding and removing from that to affect the free monad versus final tagless versus the effects. And then finally, I created a whole bunch of different interpreters. This is an example of the I/O interpreter. And what this does is it basically just takes in that calculator, which is the mutable thing that actually does the calculations. And it matches on the type. So as I said before, you match on your ADT. And it adds the number and basically just calls calculator.add or calculator.get and wraps this in I/O. So to create our actual interpreter, we just say I/O interpreter and pass in the calculator. And then we can run that using this benchmark method. And this is the method that was used across all of the different benchmarks. Basically what it's doing is it's saying I want to add the number 1, and then I want to keep adding the number 1 using these method calls. And you can see there it's basically doing a fold left and flat mapping each one of these add 1 operations. So you're basically building up a big program of add 1, add 1, add 1, add 1, add 1. And then finally, you're doing a flat map at the end where you're getting the last thing. So the last step in that program we're constructing is a get. And so when we actually pass our interpreter through, it will basically read that. It'll go, okay, I need to add 1, I need to add 1, I need to add 1. And then this is how you actually call it. And then we run unsafe run sync for the I/O in this case, because you need to actually run the I/O because it just returns the effect otherwise. So one thing to point out here, I said I'd try and make it very clear when I was running things in a sort of specific way. In this way, you probably wouldn't want to be writing your programs like this in the first place if you're trying to do something that's doing a lot of iterations in a hot loop. But what this will show is the sort of relative difference if you were to run these things at their absolute limits. So you can sort of see where the limits of the difference of performance are going to be. And then we can talk a little bit more generally about what this tends to mean in real systems. So this was the results that I got. And you can see here already, if we run with function 0 again, like we did with F monad, it's an order of magnitude faster already. It turned out, at least in my benchmarks, the cats and Scala ZIO were more or less the same, and the Scala ZIO from Scala Z7, so it's not ZIO but Scala Z7, was also extremely slow for some reason. I thought that was quite interesting. And then Future as well was also even more slow. So we'll see what this looks like shortly. I thought it was quite interesting. And then I ran the exact same thing. All I did was change the imports from cats to Scala Z, and everything ran faster. I believe there is an implementation detail that causes this. I am not super familiar with the specifics of it, but for most use cases that I've ever seen, I haven't had to worry about the thing that cats is trying to protect you from. So in general, if you want to roughly double the speed of your free monad implementation, Scala Z seems to be, at least in the versions I tested, the way to go. Now the next thing I wanted to test was final tagless. And so I created the calculator that we saw before, but with that abstract F, and then implemented it the way that we did the other one. And then the code to actually run it was more or less exactly the same. And then to actually execute it, we basically just call that, pass in the numops, which in this case was 500, and then pass in the calculator I/O interpreter or subclass. And then we run unsafe perform I/O again. And so these were the results I got for this. And I thought this was quite interesting. So this, you can see, is roughly 3 times faster. function 0, for Tagless was about 3 times faster than the function 0 for Scala Z's free monad. And so this is, as I said before, this is if you're running everything in a hot loop. So this is not probably the way you would use these things, but this shows you sort of the extremes. If you're trying to push these things to their extremes, final Tagless can go up to 3 times quicker. And just to sort of highlight what that looks like in terms of relative difference, I've highlighted just the function 0 implementations of each one because they have the least overhead in terms of the effect monad and all the stuff happening in the background. And you can see here, 3,000 ops per second, for example, in fbench versus 151,000 with final Tagless. So if you are really trying to push your application's performance while still keeping some degree of sensibility and referential transparency in all this, then final Tagless seems to be a sort of clear winner in this case. But then we'll talk shortly about how much this will actually affect your programs in practice, because it's quite interesting. Now I also plotted it on that initial graph that I did because I just wanted to kind of see how they looked, in a sort of heat map styled representation. And I noticed something really interesting, and that's that if you use final Tagless versus free monad, cats or Scala Z, versus F monad, there's sort of a clear tiering. So you've obviously got final Tagless is the fastest, free monad in Scala Z is the second fastest, then in cats is the third, and then F monad was trailing behind. But then there was a really interesting point was that Scala Z7IO and Future, the one in the standard library, was actually so much slower that it really didn't matter which one of these abstractions you picked, because it would be the bottleneck. So whenever people say that free monad is too slow to use, you have to use final Tagless, and then they say they're using futures, I kind of giggle a little bit now. So yeah, basically you're taking a 2 to 3 times performance penalty using free monad against final Tagless in its extreme form, but not necessarily in its general usage form. Now, I also was really curious, because I do a lot of work in big data, and we obviously want to try and optimize this stuff as much as possible, especially in the hot loops that are running over trillions and trillions of values. We want to reduce GC churn, we want to increase the speed that this stuff is running. So I thought, what happens if I remove these effects? What kind of cost are we incurring on ourselves by actually using these abstractions in the first place? And so I kind of stripped away most of the stuff there and just said 1 to numops for each calc.add and then calc.get. So this is that same kind of hot loop behavior, but it's without any of that effect type stuff. And the result I got was that it was 50 times faster than final Tagless. So everyone in the room already knew that it would be quicker, but I was quite shocked at how much quicker it was. And that's, just to put it in perspective, 37,000 times faster than using cat's free monad with Future, the one at the bottom currently. And then I thought, okay, what about if we optimize an imperative approach? So I thought maybe we can use the while loop and let it compile down. And because it turns out the for each implementation in Scala is not actually as efficient as it looks like it should be. And what I got was that it was now 240 times faster than final Tagless and 172,000 times faster than the slowest one of these abstractions. And so I thought, maybe I can push it even further. And so I was watching the bytecode in each one of these implementations, and this one had the absolute minimal bytecode that you can expect to do the same job. Now, obviously, this requires you to take away all your abstractions in your code. You don't want to do this generally because it becomes unreadable, especially as these things become more complex. But I just wanted to kind of get a feel for, what are the cost of these things. Removed all the objects, removed all the effects. And you might think it's not fair, but life's not fair. And so it was 413 million operations per second, which is almost 2 million times faster than the slowest effect handling one, and about 2,700 times faster than the final Tagless implementation. Now, just at this point, this is where I have to remind you again that benchmarks generally suck and that you shouldn't just therefore write everything in this kind of handwritten imperative code. But it is really telling. If you really do care about your hot paths and you really do care about performance, you need to start measuring these things, and there are definitely quicker ways that you can write your code. So some of the key observations is that the performance overhead of any of these effect structures is considerable when compared to the heavily optimized abstraction-free code. I don't think anyone is surprised by that claim, but I think the degree of difference was quite shocking to me, so potentially to you as well. Free in its extreme usage is 2 to 3 times slower on average than final tagless. Now, this is only if you use it in a hot loop. I've been kind of alluding to this, and in empirical practice, I've seen it to be closer to about 10% slower. And the reason for this is that you don't tend to write your operations in the hot loop. You tend to write the structure of your programs, so the method calls and all this stuff, and then the actual computation tends to happen in your interpreters, which is a lot more sort of side effecty and all this kind of stuff. So, obviously it depends on how you've written your code base, but it's very likely not as much of a hit as these benchmarks are sort of showing. I'd only really worry about the difference between free and final tagless if you really need to squeeze that performance out, but you still really want to keep sort of functional programming principles throughout your code base. So the other really interesting point, as I mentioned, is that the target I/O monad that you choose can make more of a difference than free versus final tagless. I thought that was really interesting, and especially as you start to use the monad transformer stacks that we saw earlier and that Harmeet spoke through. This will become more and more pronounced, so it will very unlikely to be the bottleneck of choosing free monad versus final tagless at this point, unless you're using it in a way that is the 2 to 3 times slower category of usage. And then also the Scala Z implementation of the free monad seems to be faster, and potentially someone in this room might know the specific reasons as to why. Now, the question that you're probably thinking is, how does this compare to network and I/O? Because obviously that is going to be the bottleneck of most of our applications, and how much of a bottleneck is that compared to these other things that we're doing that are just churning through stuff in memory very quickly? So I'm not sure if you can see this, but an SSD read on this is from Berkeley. They have a really cool interactive graph where you can kind of scroll through time and see how fast these things were 10 years ago up through to now, and it's really interesting to kind of see the speed at which processors have changed and the network has changed. But on this thing, we've got an SSD read in the order of about 16 microseconds, a network round trip in the same data center about 500 microseconds, a round trip from California to Netherlands is 150 milliseconds, and a main memory reference, which is kind of the space we're working in with a lot of these abstractions, is in the order of 100 nanoseconds. So you can kind of see where this is headed. Network and I/O is going to be a much bigger bottleneck than any of these things, most likely. So I ran a quick benchmark with network I/O, and it's obviously not the best thing to be doing with JMH. I mentioned it's best for its micro-optimization sort of stuff, but in this particular case, it's enough to give you a feel for the order of magnitude difference. It was 23 operations per second to read a single character from a file that I'd pre-created. So obviously, if you're doing any kind of I/O, I'd probably not be worrying too much about which one of these abstractions you're choosing. I'd choose whichever one you feel is able to best represent your business logic and effect handling semantics that you want. So, what are the implications of all this? First of all, you should definitely be measuring before you worry about any of this stuff. It's very easy to fall into the trap of micro-optimization when you see benchmarks like this, but make sure that you measure in your own code base that it is actually these abstractions causing the bottleneck, and then you can start to optimize in the ways that I've sort of shown. So I absolutely encourage you to use these abstractions to structure your programs. They make working with Scala so much nicer. It really helps as well with testability and all these other kinds of things, which is a sort of scope for another talk. What not to do, obviously, is don't use these abstractions in your hot path. You don't want to be evaluating a future call every single time you're adding to that calculator, for example. It's obviously silly. But sometimes we can't avoid it. So in the cases where we can't avoid these things, just be aware that they can be a very costly bottleneck. And also, if you're doing big data processing, as it seems like a few of you are, avoid using these abstractions directly in the bits where you're doing the big data processing. You can use them to structure your programs, but in the actual hot loops, like on the Spark executors, for example, don't use them. Not just because of the speed, but also the GC pressure is insane. So anecdotally, I was working on a system about 6 months ago, and someone fantastic at functional programming wrote some stuff that did a few object allocations to do some error handling. And it shot the heap up to something like 64 gigabytes. And then when we took that out and just put it into plain primitives, it went down to about 4 gigabytes again. So there's a pretty massive overhead in doing some of the sort of functional programming stuff that we like to do when it's at scale and when you're doing it over a lot of values. So as for the true cost of abstraction, as I mentioned, I've seen it more empirically around 10% between free and final tagless. Ultimately, it tends to come down to what you're more familiar with and what's cleaner as syntax. I've had a lot of personal experience with both of these, and I really like free monad, I really like final tagless. I think final tagless has had a lot of interest as of late, especially around some of the stuff Luca has been doing, for example. And as a result, like a lot of the things that it seemed like you could only really do with free monad and those sort of abstractions you can now do with final tagless as well. So absolutely, I think it's more about choosing whatever seems right for you and your team. I find that people who are more familiar with Java and your sort of standard Scala usage, final tagless tends to make the most sense. But for people who prefer working with data and manipulation of data, then free monad is a very natural way to kind of write your programs and manipulate them. Yeah, so unless, on top of that, obviously, if you need to reify your domain for whatever reason, free monad does that by default. You can do it with final tagless, but you do it by turning it into a free monad. So if that's an extra step that doesn't need to happen, maybe it actually makes more sense to use free. But yeah, that's basically all I have for today. Thank you very much. Any questions?